Good morning, good afternoon, good evening, wherever you may be in this part of the world. Welcome to another interesting presentation topic. And this time, the topic is typical testing performed on a gas insulated switchgear. My good name is John Kweku Amu-Otu, and I've been a professional electrical engineer for the past 31 years. I'm based in the United States of America. Now let's talk about the outline, right? Okay, so as part of the outline, the first item on the outline is we'll talk about what is a gas insulated switchgear and when do we use it, right? Then typical nameplate details of GIS. So basically, we'll walk through all the nameplate parameters that basically is required for the GIS, and usually the nameplate details is stamped and stenciled on a plate after the factory acceptance testing, and it becomes part and parcel of the GIS throughout its operating life cycle. Next is we'll talk about the different external connections of GIS. Okay, so the GIS can be externally connected to an overhead line or a power transformer. So we'll take a look at all the connections to externally to all this equipment. Next, we'll discuss all the components of a gas insulated switchgear. Then, to perform testing on a GIS, right? Okay, so because the gas insulated switchgear is a complex equipment, high voltage equipment, right, for the modern, and it is compartmentalized. It comes in the form of modules, right? And it is filled with SF6 gas, sulfur hexafluoride, right, at high pressure above ambient. As such, assessing the required testing connections that is required to perform the testing on the GIS when it is due, let's say after 10 to 12 years, or in between that, if there's a problem with your GIS, it becomes a challenge, So basically, you setting access point has to be derived, and we'll talk about all those access points that is far away from the SF6 filled compartments that you can perform quite closer and accurate testing for the GIS. Next, we'll talk about the typical inspections and testing that is performed for the gas insulated switchgear. And usually, each manufacturer comes up with its required inspection and testing. And most often than not, the testing and inspections are based on the number of operations of the circuit breaker, the edge switches, the disconnect switches. So you can obtain all those information from the cyclometer reading or your maintenance history of the GIS, and also the number of faults that the circuit breaker has encountered. Next, let's talk about what is gas insulated switchgear and when do we specify or implement its application. The first thing is a gas insulated switchgear basically comes in the form of metal enclosed switchgear, and basically it is compartmentalized and modularized. It comes in the form of modules, and it is filled with high pressure SF6 gas. Comparably to AIS, the gas, the insulating medium that is filled in the GIS has a high dielectric capability compared to an air insulated switchgear. Because it is compartmentalized, basically comes in the form of modules. Basically, let's say if faults should occur in each in a module, it doesn't basically escalate, or it doesn't basically transfer it to the compartments or modules. As such, the fault is much localized, and basically you can basically isolate that bay and basically resolve a fault that is there. Okay. So now let's talk about when do we specify and implement the GIS, right? Okay, that is very important as a discipline engineer, where you have to make a decision when to use an AIS substation or a GIS substation. Okay. So one of the first reasons is if you have a congested city, highly populated density city, right? If you have a city that's choked with buildings, there's no space in it, right? Okay. So if you have such a situation, right, building an AIS substation, air insulated substation, it's not the best choice, right? Because space is a premium, right? Okay, so your best choice is gas insulated switchgear, which is basically has a smaller footprint, and basically it comes in the form of compartments, and also to talk about the safety part, because you have a highly densely populous city, right? And the GIS offers more of safety compared to an AIS. And in terms of reliability, too, basically the GIS has a higher reliability than the AIS. Next is a very compact, and that is perfectly true, right? Because I made mention that it comes in the form of compartments, right? Okay, it is in the form of modules. That's how it is shipped before it is assembled in the field. And as such, if you have a highly congested city, right, where space is a premium, and basically, it becomes the ideal choice for you to specify a GIS so that it can fit in tight spaces and blends with the environment. Next is I'll say that most often it is maintenance free. So that is the slogan that the manufacturers will tell you, and it is partially true, or quite close to the truth. But it all depends on the first 10 to 12 years, how you operate, how you follow the manufacturer's instructions on to operate the GIs to achieve that maintenance-free slogan that they are indicating. Because a lot of the problems start creeping in right after the 10th to the 12th year, right? That is when you have a lot of problems, excessive leaks, and also PD activity, etc. Next is reduced installation time, and that is perfectly true. As you can see, in the factory, right? Okay, before, if you have a greenfield project, right, and you because it comes in the form of modules, right? It is compartmentalized, right? Okay, before it is shipped to the site, right? It makes installation much faster, right? So it results in reduced installation time, and that is what every project that is out there requires, right? So you're able to achieve reduced installation time to meet due dates of your project. Next is reduced cost of maintenance. Yes, and that is perfectly true, right? Okay, so for a GIS, right, if you follow the required maintenance, the required operation requirement that is specified, that is delineated by the OEM, right, you will achieve a reduced cost of maintenance, because during the first 10 to 12 years of each operation, most of the maintenance that you can perform is predictive maintenance, that is visual maintenance and data collection, right? And based on data from the cyclometer of the disconnects, which is the circuit breakers, and also information from the SFS gas, right? So, as such, comparably to an air insulated switchgear, where every year, every 3 years, every 6 years, for instance, every 6 years, you have to perform time-based maintenance, which basically requires a major outage and taking a lot of the equipment. Look at the number of equipment that is in an AIS and larger footprint. Basically results in a lot of labor cost and parts cost. So basically, GIS is able to achieve a reduced cost of maintenance. And matter of fact, beyond that, it allows you to achieve a life cycle cost of maintenance, which is very good for life cycle modeling for your asset management for the GIS. Next, reduce footprint, and that is perfectly true, right? Okay, so because everything is in the form of compartment, right, and also because the insulating medium that is utilized is SF6, right? Comparable to air, you're able to achieve a smaller dimension, smaller footprints of in all the internal components. As such, the overall footprint is smaller and can fit into tight places. Okay, as you know, sometimes in a highly polluted environment, and where is a highly polluted environment? That is from an industrial facility, that is oil, gas, and other industrial industries that is out there, that emits a lot of pollutants, salty pollutants, oil, dust, and sand, etc. So if you have an air insulated substation, right, what happens? basically these pollutants are going to impinge on the insulators, the apparatus insulators, the support insulators, the equipment themselves, and also all the connection points of the live connection points. And what does it do? Basically, it can result in the flow of a leakage current. Basically, the leakage path to ground is reduced and can result in the flashover. But you cannot have that in a gas insulated switch because everything is in a metal enclosed and it is compartmentalized, filled with pressurized with SF6 gas. As such, that GIS becomes the best choice and ideal candidate for an environment that is highly polluted. Next is a reduced project risk, and that is true, right? Okay, in a construction environment, you are installing a GIS, right? Okay, so you are able to achieve a reduced installation time because it comes in the form of modules, right? Okay, so you're able to reduce the project risk in meeting due dates, right? And also the budget. You're able to meet the budget, the required budget that is required, comparably to an AIS substation. Next is excellent safety, right? Because everything is in a metal enclosure, right? All the live parts are basically fully enclosed, and basically it is not accessible to personnel, operating personnel, maintenance personnel, right? Okay, so basically it offers an excellent safety for personnel that comes into close proximity with this component. Next is approved, right? Okay, because it is compartmentalized and filled with high pressure SF6. Basically, the SF6 is able to extinguish that arc. On the other hand, you're also able to view the position of the switch. There's viewports, right, that allows you to basically see the open-close position of the switches, the disconnect switches, the circuit breakers, without basically assessing the live parts. Next, lastly, it is also able to offer the lockout and tag provision, right? Okay, that's if you want to take an outage in a day, it basically provides an easy lockout tag that you can hang your tags and also your locks. Next, let's take a look at a typical nameplate for a gas insulated switchgear. Like I made mention that a nameplate is like a birth certificate for any high voltage substation equipment, right? That is part of the operating life cycle of the high voltage substation equipment. So let's take a look. The first thing is a GIS that is rated at 420 kV, right? Okay, so this is the maximum operating voltage, right? Okay, so in achieving the maximum operating voltage, right, a factor of plus or minus 5%, right? Okay, so let's consider over voltage, that is 5% above the nominal voltage of 400 kV. So your nominal voltage for this one is 400 kV, right? And if you 5% of that basically allows you to achieve 420 kV. So next is the rated power frequency withstand, right here. Okay, and what does that mean, right? Okay, so the ability, if that you have a fault condition, an external fault condition, and after the fault clearing, right, there's an over voltage, a power frequency voltage, right? This is the withstand capability of the GI 650 kV. Next is lightning impulse withstand voltage. If you have a GIS that is located in close proximity to a lightning strike, right? Basically, those lightning impulse has a very high steep front, right? Okay, then basically tailored to 50%, right? Okay, so right to achieve 90%, it is a very steep front, right? Okay, so this is how much the insulation has been built to withstand. So it's able to, because lightning impulse basically delivers a lot of very big high over voltage. Basically the GIS and its insulation system has been built to withstand that and protect the internal component of that. Next is a switching impulse surge, right? Okay, so during opening and closing of a circuit breaker that is in close proximity to the GIS, or internally if you are opening and closing the GIS, right? Okay, so it basically emits that over voltage condition, right? And this is how the insulation system and the components of the GIS has been built to withstand. This is how much voltage they can withstand. Next is the rated frequency. Okay, so worldwide we either have 50 Hz or 60 Hz, right? Then the bus bar current. Okay, so for a GIS, right, we have a horizontal bus bar, phase A, phase B, phase C, right? Okay, so the rated current for this one is 6,300 amps. Then the feeder current for is basically the one side, the line current that is going to the load, right? Okay, so that's how much the feeder can withstand. That is 4,000 amps. That's the rating of the feeder or the line current. Next is the rated short time withstand current, right? Okay, so short time basically is either 1 second or 3 seconds, right? So that is basically the symmetrical short circuit current. So that's how much short circuit capability that it can withstand when a short circuit should occur in each compartment or the overall compartment of the GIS. Next, let's move on to another GIS that is rated at 220 kV, right? Okay, so this GIS has been built with a rated voltage all the way up to 300 kV. So basically, a lot of multiplier contingency has been built into this. Okay, usually sometimes you can go like more than 10%, or depending on the customer's specification. Right? Okay, so for the rated power frequency withstand voltage, we are having 460 kV, and like I said, for the power frequency withstand voltage, that comes into play when we have an external fault. That comes into play that after clearing, it results in over voltage. Or let's say if you have a load rejection, that can result. Or let's say if you have a no load condition, which basically can also have an over voltage condition. So the GIS insulation system and the components has been built to withstand this power frequency over voltage condition. Next is lightning impulse withstand, right? And this is the amount of over voltage that it can withstand due to a lightning strike. Next is switching impulse due to operation of a circuit breaker, open and close, and the rated frequency, either 50 Hz or 60 Hz. Rated continuous current, that is for the bus, right, and also for the line side, the feeder, right. This is how much capability it's rated, and also the short time withstand current, that is 1 second or 3 seconds, right, 50 kA. Next, let's take a look at another Siemens switchgear, right? Like I indicated, this is the passport for the equipment. This is the best certificate for the equipment throughout the whole operating. So basically, this is basically the year of manufacture. This one is saying 2015 right here, and this is the serial number. Okay, so anytime you want any information on this GIS, right? This is the serial number that you need to contact the manufacturer. So once the manufacturer plugs in this serial number, it tells, basically it provides everything, all the engineering documents, all the simulation studies, all the design documents, right? All the 1 line, the 3 lines, the factory acceptance testing, all the basically in-stage manufacturing quality testing that was done on this GIs will come up, right? So that is how the manufacturers usually utilizes the serial number to access every information. So anytime you want to contact your manufacturer, utilize the serial number. Next is the rated voltage, right? Okay, so this one, the nominal voltage is 69 kV, right? And the maximum is 72.5 kV. So as you can see, it's about plus 5% above the nominal. Next is your rated lightning impulse withstand voltage, right? 325 kV. The power frequency over voltage, 170. The rated frequency, 50 or 60 Hz. Then your rated normal current for the bus bar or the bus coupler. The bus coupler is usually a tiebreaker that ties, let's say if you have 2 bus bars, right? And in between that, you want a tie in between this. That is when you utilize the bus coupler to tie the 2 buses. Next is the line side, the feeder. That is the rated current for the line side. Then the short circuit current. Next are the different external connections to your gas insulated switchgear, right? Okay, so the first one is your it's an overhead connection, right? Okay, so this one is a single phase arrangement. Okay, so for a 3-phase view or a dimension, you can have a phase A, phase B, phase C, right? On overhead coming in, then basically they get connected over here, right? So this is what they call apparatus bushing. That is the industry word for it. Industry technical word for this. Okay, so it can either be a porcelain or polymer. Right. Okay. Within the last decade, right, 10 years, right, okay, most utilities or industries are shifting from porcelain to polymer, whilst others are maintaining the status quo, right? So one use porcelain for many reasons, right? Okay, so each technology has its own advantages and disadvantages, and I'll walk through uh, the advantages and disadvantages of each one. Okay, so for the porcelain, right? Okay, so on the surface of this, right, there's something they call sheds, right? Yeah, right. It's going like this. Okay, so that's how they call, it's been arranged. So it's more of a shed, or there's industry terminology that they use that it is in the form of skirts. Right. Okay. So the reason why on this surface it's been arranged in the form of skirt, it's because it increases the creepage distance to ground. Instead of a direct distance, right? What it's doing is basically the leakage current is traversing this path like this, on the surface of this. So in that instance, it is increasing the distance for a flash over. So as you are increasing the path to ground plane of the leakage current, basically you are preventing or mitigating a flash over, right? So that is all this is about. Okay, so the porcelain has a lower hydrophobicity. So hydrophobicity, what does that mean, right? That is an industry technical word for a phenomenon, right? It means that it doesn't have the capability to repel contaminants, right? If you have this type of bushing located in an environment where there's an industrial facility, right? Oil contaminant, dust contaminant, sandy contaminant, salty contaminant, right? All of them are going to form on the surface, right? So this porcelain does not have that capability. So all the contaminants are going to form on the surface. So with a lot of raindrops, or basically, then you have a leakage current flowing, right? Leakage current flowing, and can cause a flashover. So that is one of the disadvantages or the drawbacks of this type of bushing. Secondly, if you have somebody throw a stone at this, because the porcelain is made from a powder material, right? Clay, right? It can chip, it can break. And if it breaks or it chips, what happens? You have an external element of the weather, moisture, intruding into the SF6. Remember, the SF6 is acting as an insulating medium. In here, right, is going to intrude and basically degrade the integrity of the insulation medium. And you can have all sort of basically PD activity, etc., right, inside this medium. So that is one of the disadvantages or the drawbacks of the porcelain insulation medium. One of the advantages is its robust mechanical strength. It has that mechanical strength to withstand higher temperatures. Secondly, the other technology is polymer, right? That's what I indicated, that a lot of utilities or industries are shifting to polymer insulation, right, from porcelain, because of advantages that the polymer has. The polymer has a high capability of hydrophobicity. right, the ability to repel contaminants from forming on the surface of the insulation. It forms water beads, right? It does not form a continuous film like porcelain forms. So it forms beads. As such, it is not continuous. As such, contaminants are repelled, and it prevents leakage current from flowing to the ground plane and prevents a flushing. So that is one of the advantages. That is why a lot of our utilities are shifting from porcelain to polymers. One of the drawbacks is its flexibility, right? It is very soft, as such that sometimes birds with longer peaks, right? Like eagles and all those things can poke into the flexible sheds and eat on it, and basically it destroys them. And sometimes too, if it is located in an environment that has a high temperature, basically it's going to start degrading. Right? So this is an air to SF6, right? Okay, so in here on this side is air. In here is all filled with SF6, all the way. Okay, so now let's talk about the components, right? Okay, so we have an enclosure that has a bus here, right? That is filled with SF6. We have the disconnect switches. We have an Ethernet switches. We have the CTs. We have the circuit breaker. We have the breaker operating mechanism, right? And up here we have the bus, right? So this one we have a double bus arrangement, right? Phase A, phase B, phase C on the side, and phase A, phase B, phase C on the side. Okay, so that's what you see for the double bus arrangement. Another external connection that you can have is a cable feeder, right? Coming from here. If you have a 220 kV, 380 kV feeder cable that comes in here, right? That is connected to this SF6 chamber, right? Then from here, it is all filled with SF6, right? All filled with SF6, right? So this one is an air on this side, then SF6. So this is an air to SF6 interface or interchange, right? Okay. So similarly, this is a double bus arrangement, right? Phase A, phase B, phase C, right? Okay. So as you can see, this is the VT, the voltage transformer that is utilized for mirroring and protective relays. Then CTs are over here, and this is the breaker operating mechanism. Another external connection to a GIS, right, is an integration to an oil transformer. So if you have a transformer that is here, right? Okay, so like I said, this is a single phase arrangement, right? In a three-phase arrangement, we can have phase A, phase B, similar, phase C, right? Same, similar arrangement, right? Okay, so we have oil here, right? So this one is oil to SF6. So all this part is filled with SF6. All this part is filled with SF6. Okay, so this one is an oil to SF6 interchange or interface. Next is a bus coupler, right? Okay, so a bus coupler, like I indicated, right? If you have a double bus, right? Okay, then in between that, it's a breaker, a tie breaker, right? Okay, so the tie breaker is the one that couples these two buses together, right? We have bus A on this side, bus B on this side. We have bus A on this side, bus B on this side. So the tie breaker is what couples bus A to bus B, or bus 1 to bus 2, right? And we utilize that scheme when we close the tie breaker is when we want to take one source out and have these two buses being fed with a single source. Under normal circumstance, when this one is open, this bus is fed from here, and this bus is fed from here. Once we close the tiebreaker or the bus coupler, then only one source comes into play. Right? Okay, so that is also another external connection that we can have where the tiebreaker can be fed from here. Right? We have a feeder that comes in here and basically feeds these two buses. Next, let's go through a single line diagram of a gas insulated switchgear. Okay, so basically, like on the previous slide, right, we went through a double bus arrangement. Okay, so this is a bus, right? It is in an enclosure. This is the enclosure. All this enclosure is filled with SF6 gas. Similarly, this is the second bus, right? Inside the enclosure, it is filled with SF6 gas, right? So, the SF6 gas, what does it do? It's basically creating an insulating medium and also a dielectric strength to basically insulate the live component and also to interrupt any arcing that will occur in the enclosure, right? Okay. So we have a circuit breaker that is here, right? On each side of the circuit breaker, we have a disconnect switch, right? Then on this side is a disconnect switch, which can be earth, right? And this disconnect switch can be grounded. So basically, this is where the earth switch comes into play, right? And these are instrument transformers, right? Okay. So this one, for instance, is the VT, right? And the one in series with the breaker is the CT. Okay. So similarly on this diagram, right? Okay. Similarly, double bus arrangement, right? We have a disconnect switch, right? We have an earthing switch, and we have a circuit breaker. On this side is also another disconnect switch, earthing switch, and VT and an earthing switch are basically the line side. We have a line disconnect and the line earthing switch. Same like we have a bus disconnect switches, then we have a bus earthing switches. Okay, so now let's talk about this diagram, right? Okay, so this is an apparatus bushing, right? And I went through that with you on the previous slide. So I explained how this is in the form of zigzag. It's to increase the creepage distance and also prevent leakage current from reaching to the ground plane. Remember, this is a flange here, right? And that is ground plane, and the goal is to prevent leakage current from reaching there faster, and basically to preventing a flashover. Okay, so you can have an overhead line come here and basically get connected over here, right? All this is filled with SF6 gas, right? And within this enclosure, all of them is filled with SF6 gas, right? Okay, so this is basically the disconnect switches, right, for each phase. Phase A, phase B, and phase C, right? This is the circuit breaker, right? And this is the operating mechanism for a circuit breaker. So the operating mechanism, you can have a hydraulic system that utilizes a hydraulic oil, right? Okay, so pressurized hydraulic oil, which basically compresses a spring. So the spring is charged. That basically operates the circuit breaker, right, from the open and closed position. Okay. So similarly, we have basically on the line side, right, we have disconnect switches and earthing switches, and the CTs are located over here, right, and this is the BT that is located over here. Next, I think I went through this scheme on the previous slide. Okay, so this one is apparatus bushing, right, called SF6 bushing. It is filled with SF6. From this side, we have the overhead line, the air side, right? The air side is this, and this is the SF6 side. Okay, so this is basically a bus, right? That is inside an enclosure. The enclosure is all filled with SF6 bus. And remember, I made mention that it is compartmentalized, right? Okay, so this compartment, as you can see over here, is separate from this compartment, right, through a barrier. So there are barriers that prevents, basically when there's a problem here, it doesn't basically come here. When there's a problem here, it doesn't come here, and vice versa. Okay, so this one is the VT, the voltage transformer, and disconnect switches, earthing switches, right? Then the current transformer, the circuit breaker, the operating circuit for the circuit breaker, right? Disconnect switches, Now let's take a deep dive into what the circuit breaker operating mechanism is. This is an example of a hydraulic spring system that is shown over here, right? Okay, so this one, each one is operating a circuit breaker. So as you can see, the number of circuit breakers that each hydraulic operating mechanism is integrated to. Okay, so this is the horizontal basis, right? As you can see over here in the disconnect switch is also shown over here. Okay, so basically this one is utilizing hydraulic system, utilizing pressurized oil, right? And that is integrated to a spring system, right? So the spring system is compressed and charged, right? So once it is charged and compressed, it is integrated to the linkage, mechanical linkage of the circuit breaker, right? So that is what basically, you know, the linkages are interconnected and basically operates the breaker to an open or closed position. Okay, next slide. I indicated that we have a disconnect switch, right? Okay, so as you can see over here, we have the horizontal bus system for the GIS, right? In a three-phase arrangement, right? Okay, to operate the disconnect switch, right? The GIS gives you the capability to visually see the status, whether the disconnect switch is in an open position or closed position, right? And this is basically a visual port, right? That gives you the ability to see the status of the disconnect switches. So that this part is basically the part of the safety part, right? That delves into the benefits of the GIS, in that personnel do not come into contact with the live components that is inside the enclosure. Now, let's talk about basically go through, this is a typical Siemens, GIS, right? Okay, so as you can see over here, this is a picture of the voltage transformer, right? Okay, so for a voltage transformer, right? Okay, let's say you have a bus voltage, primary side voltage of 220 kV, or a primary side voltage of 300 kV, or up to 800 kV, right? Okay, but this one looks like 69 kV, right? Okay, so this VT basically scales or steps the voltage down from this high voltage to 69 volts, line to neutral or line to ground, or 115 or 120 volts, line to line, to be used by protected relay elements, right, or mirroring elements. So this section is basically the CT, right? The CT is like indicated, basically integrated to the circuit breaker. Okay, and this side is your line control cabinet, LCC. Okay, so the line control cabinet is your interface between any field equipment like power transformers, right, and your SCADA or DCS system, right? And all the modules and components are all integrated here. As you can see over here, all the wiring coming from all the components, all of them basically gets integrated on this LCC cabinet. One of the key features of a GIS, and matter of fact, one of the benefits, it's this barrier, right? This barrier, and usually it is colored. It can be in different colors, right? The manufacturer usually indicates to specify those barriers. So what those barriers, they are all sealed, tightly sealed, or tightly sealed barriers. What it's doing is basically it is separating this section from this section, right? So the SF6 gas that is filled here is different from the SF6 gas pressure. Maybe it could be that different pressures based on the component that is in there. But when the benefits of this sealing is when there's a problem here, this sealed barrier prevents this problem, the problem that had occurred from here, from basically cascading or moving to and spreading all around the switch, the GIS gear. Now let's take a deeper look into an enclosure, right? Okay, so let's say this enclosure, as you can see over here, this is what is inside this enclosure, right? Okay, we have a bus, and inside here is all filled with SF6 gas, right? Okay. So we have a gas density monitor that basically allows you to monitor the pressure or the density of the gas, SF6 gas, that is in there, right? If there's a leak somewhere, right, you will see it, based on what is indicated here and what is your alarm point and your cutoff point that basically you have set, integrated into your SCADA system or your real-time monitoring system, right? Okay, so usually your real-time, the setting for this is basically your required pressure, your minimum, let's say your minimum and maximum, and your cutoff. Well, cutoff is basically when the gas pressure drops to a certain level. That is when basically the breaker fails to operate because the gas pressure has dropped to a certain point that it cannot operate. Next, it's a pressure relief device, right? Okay, so inside this enclosure, right, you can have an overpressure condition due to a fault, right? So this pressure relief device, PRD, is what helps to relieve that pressure that is in that enclosure, right? Just like the pressure relief device that you see in a power transformer that is located on top of a power transformer enclosure, that when a fault occurs and all the protection systems that are in place to protect the transformer, if all of them fail, right, and because fault current is electromagnetic and dynamic in nature, it evolves, right? It grows and grows into a big force and big pressure inside. As such, the pressure relief device is for the transformer is the last resort, and basically it opens and expunges all the oil from the transformer onto the floor. Right. The goal is basically personnel safety. Right. Okay. Then all these are supports, right? Okay. So as you can see over here, we have a bus system that is running horizontally. Definitely, you need a support that can hold this bus to be in horizontal place and to be in place. Okay, so these are barriers, right? Okay, remember I made mention that there are barriers over here that basically protects this section from this section, and this is how the barriers are shown. Next, let's talk about the SF6 gas, sulfur hexafluoride. SF6 means sulfur hexafluoride. Okay. This insulating medium, like I indicated, is far better than air, right? Okay. Though it basically creates global warming, politics, issues, and a lot of nations and utilities and different states in the United States are all shifting from SF6 gas as an insulating medium to alternative gas, SF6 free. SF6 gas, has been good, and basically has a high dielectric properties 3 to 4 times that of air. So this table basically gives you a typical filling pressure, right? Okay, for the different components of it basically tells you the filling at 20 degrees Celsius. Okay, so what the manufacturer, this is basically at the factory level, right? At the factory level, basically they're able to simulate and obtain a factory temperature of 20 degrees Celsius, right? Okay, so what the manufacturer gives you as part of its instruction and operating manual are basically the SF6 gas at different temperatures, right? So what you have to do is you have to, at the time that you are filling the SF6 gas, let's say if you have an SF6 gas leak, right? what you use is you use that chart that the manufacturer provides you as part of the instruction manual to based on the temperature, the ambient temperature at that time that you are filling the SF6 gas to determine the pressure that you are supposed to fill the GIS. Basically, the pressure is going to be scaled, right, based on the ambient temperature at that level, at that time that you are filling. So basically, it gives you the filling pressure, the minimum pressure, right, you can achieve, right? So basically, your alarm system at your SCADA, right? Once basically you have a maximum, right? Your filling pressure and your minimum, right? So once your pressure starts dropping, as it starts getting close to your minimum, then it will start giving you an alarm for you to investigate, right? One of the things that you want to do is investigate and validate whether it is truly an alarm condition, gas leakage, SF6 gas leakage, right? Okay, so one of the things that most call out basically it's basically investigate whether it's true or not. Once it is true, as after you validate, you do all your testing, your leakage testing, utilizing other testing portable device, then you have to fill it with SF6 up to the maximum level. Right? So as you approach the minimum level pressure, let's say if you have an SF6 leak, right, then that is when you receive an alarm. And I made mention that when you receive the alarm, you have to investigate and validate the alarm. Next is your minimum response, right? Okay, so this is when basically your circuit breaker contacts basically locks out. It means that the pressure has fallen to that level that it is not going to operate. It is not going to operate. Right. So when it falls to that level, then if it is truly a legitimate alarm leakage, then basically you basically have to tie in the OEM and basically investigate and basically implement the required corrective action. Okay, so I took a rundown of this picture. I indicated all the components and of the circuit breaker, the LCC cabinet, the voltage transformer, and the CT. So this one is the line control cabinet, or the local control cabinet. Excuse me, the local control cabinet, also called LCC, right? Okay, so like I told you that this one is the interface between any adjacent interface equipment like the power transformer, right? Transmission line, and the GIS, and your SCADA system, right? And any downstream, your line side equipment, like any feeder that is going to the load, right? The customers, right? Any equipment. If you have a switchgear that is there, medium voltage, it goes through a power transformer, steps it down to a medium voltage switchgear. All of it, the interlocks are all tied to this one. Right. Okay, so this also close to this one should be a protective relay panel, right? That has all the protective relays that protects your line feeder, right? So your line feeder, you can have a differential protection, right? You can have a distance protection if you have a transmission line on that feeder, on that line feeder, right? This section is your bus. Usually, because the GIS is much more compartmentalized and filled, usually bus differential, unless of course the customer specifically indicates that they want a bus differential, but most of it are not. The GIS don't have a bus differential, but rather have a line protection for the bus, for the line side. Okay, so for the line side, you have a differential protection, 87 L. Then you have your distance, right? You can have your distance phase and distance ground or neutral, right? Then sometimes you can have a directional phase and directional neutral, in 50, 51 instantaneous overcurrent and time overcurrent on these feeders. Right? Okay, so as you can see over here, right, on the line local control cabinet, right, you can see these are the metering, right, indications, right, that tells you your voltage and your current, right? Okay, so as you can see over here, right, this is a typical one line in each bay. So this has 3 bays, right? Okay, so this basically in front of the local control cabinet is basically your one line. It goes through all the disconnect switches, all the Ethernet switches, all the circuit breakers. Basically, it gives you a pictorial view of what's inside the bay of the GIS. And this one is equivalent to the approved for construction after construction the single line drawing that you have. So for the current transformer, right, this is the enclosure, right, okay, of the current transformer. So the CTs that you have, right, okay, so let's say you have a 4000 is to 5 CT, right? The relay or the mirroring circuit needs only 5 amps, right? And sometimes you can have 1 amp, right, CT on the secondary side current for your meters for your protective relays. Okay, so this is in close proximity in series with your circuit breaker. This is basically your ceiling end. Okay, so this is the gas tight barrier that basically differentiates this section, protects this section from this section. Next is the line side, right? Okay, so the line side basically have cables that has been installed in this compartments, and basically as you can see over here, this is what they call cable sheets, right? Okay, so as part of any cable, right? Okay, so you have a cable that is rated for, let's say, 2000 amps, right? That's the line side cable, right? Okay, as part of the cable configuration, we have a cable sheets, right? So nominal current basically goes through the conductor of the cable during normal operation, right? But when there's a fault, right, then this is the path for the fault current, right? Because this one has a very low resistance path for the fault current to flow to ground and to the substation grid, right? This is bonded to the equipment, right? And from there, it goes to the substation ground mark, right? From here. Okay. Okay, so I showed you a picture of this earlier, and I showed you all the components of it, and basically how all of them gets are wired from each component to your LCC cabinet. And I also showed you your line side cable feeders. One of the things that I want to talk about is your high-speed edge switches, right? Okay, I indicated that sometimes if you have a lightning surge, right, external lightning surge, that basically intrudes, right? Okay, on the line side, there are high-speed edge switches, basically that takes those charges to or high voltage to ground as fast as possible, right? Okay, then sometimes to if you have an over voltage condition or basically a fault in a component or a module, basically you have a high-speed edge switches that basically takes the energy to ground to prevent the energy from cascading into other components. And usually a lot of times this is basically the external interface. That is where the high-speed edge switches come into play, because if the switchgear is the GIS basically is interface with the external side. Just this is an example, right? You have an external, the load side, right? So if you have the load side, that's an external component, and the incomer side, okay, the external incomer side is an external component. So those are where the high-speed edge switches are going to be located, basically to take all the energy from this phenomenon, lightning surges, capacity coupled voltages, over voltages to ground, for prevent it from cascading into other components. Okay, so next is basically, as you can see over here, I showed you that the edge switches, right? The disconnector edge switches are basically the best access points to perform your testing, right? Okay, so this is an indication. So you see that there's going to be a window here that basically will show you, its position and also how to access those edge switches. Okay. So as you can see over here, this is a typical maintenance switch that is basically that allows you to basically ground that switch, and also basically, if you want to perform testing, to remove that connection and inject whatever testing device, connect that testing device that you want to perform. Okay, so this location basically shows you your feeders, right? Okay, so this is how your line side cable are connected into this apparatus portion. So all this side is filled with SF6, all everything is here. On this side is the air side. Okay, and this is the PT. This picture also shows you, different connections for the F switch, right, for a different manufacturer, and another manufacturer shows you how these are connected. So this picture also shows you another F switch, and basically how they are connected to F. Okay, and this side shows you the how this F switch has been removed. Remember, I told you that is the only access that you can use to perform testing of the GIS, because there's no way you can assess the internal components of the GIS. So basically, you remove the links and you basically connect your testing equipment to perform your testing. Okay. So this picture also shows you another manufacturer that shows you how the head switches, head switches are connected to ground. Okay, so now let's take a look at the typical inspection and testing that is performed on the GIS. So this usually comes into play right after, let's say, 10 to 12 years when the GIS has been in operation, right? Okay, so that's when you basically perform the circuit breaker. For the circuit breaker, you perform the circuit breaker timing test. Then you also perform the close and trip call current and voltage test. But remember, there's a minimum and maximum voltage. Okay, let's say if you have a DC voltage that is being applied to operate the close and trip coil, right? Okay, let's say if you have a substation with a 125 volts DC battery voltage that basically provides voltage to the close and trip coil, or if you have a substation that has 48 volts DC, there's a maximum and minimum point that these close and trip coil are tested to make sure that at least they pick up above the minimum, because that itself guarantees its reliability to be in service and also operate reliably when basically it is in service. Next is the motion travel analysis. Okay, so motion travel analysis testing is performed for the breaker mechanism and also for the contacts. So because that is basically a slow motion analysis to find how basically the contacts are operating. So basically it's more of a velocity. So the velocity is determined and basically compared with the factory acceptance testing or the manufacturer's recommendation. Then also for the motor current, right? Okay, basically, the current that is drawn by the motor is also tested. Yeah, because that is very important, because if the motor draws high current, then that itself tells you that there's an internal short in the motor. In addition to that, insulation resistance also is performed. Testing is performed for the motor to make sure that the motor insulation is intact and the integrity of the insulation is high. Next is contact resistance, right? Okay, so a breaker has a contact, right? Stationary contact and movable contact, right? Okay, so during when the breaker is in closed position, basically the movable and the stationary and the movable contact are basically integrated to each other, and in the open condition, that is when the movable contact basically pulls from the stationary contact. In pulling away from the stationary contact, that is when an arc is created. And the goal of the SF6 is basically to extinguish the arc that is formed to prevent recovery of voltage. Because as you know, recovery of voltage is not ideal for the circuit breaker. Next is inspection of the breaker mechanism. Okay, so the inspection of the breaker mechanism is done. Usually that is recommended after the manufacturer will specify that inspection to be done. After certain number of operations of the breaker mechanism, certain operations of the circuit breaker, right? Okay, so let's say if the manufacturer says, okay, if your circuit breaker has operated for 5,000 cycles, right, within the 10 to 12 years, then I recommend a major overhaul for your breaker mechanism, your breaker operating mechanism. So that is when they will basically take everything apart, inspect, and clean everything for the breaker mechanism. So it's all based on your cyclometer operation of your circuit breaker. That is when you can move to that step. Because remember, on one of my presentations, right, where basically this GIS, right, has been in operation for quite close to 10 years to 12 years, right, and the circuit breaker cyclometer reading was reading about 100, right. So that itself tells you that far away from 5,000. So basically, inspection of a breaker mechanism, it's not necessary at that time. The GIS was due for a major overhaul. So that itself is based. A condition-based assessment can basically extend the time-based maintenance from 10 to 12 years to 15 years. So that was one of my recommendations that I made on that presentation. Next is disconnect switches, right? Okay, so as you know, you have a breaker, right? On each side of the breaker, definitely you're gonna have a disconnect switch, right? You're gonna have a disconnect switch, right? Okay, so because once you interrupt the breaker, right, there's gonna be capacitively coupled charges, right? Okay, that you can use to open this circuit breaker. This circuit breaker, this disconnect switches, right, over here. Once you open the circuit breaker, then you can operate the disconnect switch, because this disconnect switch is no load operating disconnect switch, but it has a certain capacitive current that it can break, right? Let's say about 0.5 amps, right? Okay, so that's when you open to isolate the side and the side. Okay, then you have an earth switch, so that is when you ground the bay to basically mitigate other capacitive stray capacitive charges that might be floating around on the GIS bay. Okay. So there are motors that operate these disconnect switches that are on this side of the circuit breaker. So this is the line side, right? Similarly, for the bus side, right, we have disconnect switches, right? And there are motors that operate. Same applies to the earth switches, right? There are motors that operate. So they perform motor current. How much motor current testing. Basically how much it is drawing. Then they perform insulation resistance testing, right? Let's say 1,000 volts DC testing, right, to find the insulation resistance testing. Then basically smaller motors like that, at least 10 to 100 mega ohms is an acceptable insulation resistance result for that. Then contact resistance, right? So we have a disconnect switch, right? Okay, so when it is in closed position, right, contact resistance is performed to make sure that the disconnect switch is fully seated and it is not partially seated. Because when it is partially seated, it creates a high resistance point at this point and can create heating when current is flowing. And that heating itself can destroy the, can create an arcing and basically can create a, destroy the insulating medium, the SFX insulating medium that is in that enclosure. Next is inspection and testing of the current transformer, right? So for the current transformer, what testing is done? Insulation resistance testing, right? To test the insulation medium of the city, right? Then turns ratio testing is done, right? Then magnetization testing to test for the saturation of the city, right? Then also polarity testing is done to test the city polarity. Next is voltage transformer, right? For the voltage transformer, turns ratio is done, testing is done, insulation resistance testing is done, right? Then winding resistance testing is done. Same applies to the current transformer. Winding resistance testing is done, right? Then polarity, then phase shifts testing is done. Then for the SF6 gas, right? Okay, so the SF6 gas, PD activity, for the, especially when you have an environment, contaminated environment, then PD becomes a problem for you to fight. So, and also if you have a leaking SF6 gas, that is when the elements of the weather, intrude, moisture and all those things, intrude into the SF6 that is in that enclosure, and basically can create a PD activity. So PD, partial discharge testing, is done to make sure that you don't have a PD activity anywhere. And even if it is done, there are ways and means where they perform localization to identify the exact area that the PD activity is taking place. So now let's take a look at how the testing is done, right? Okay, so if you take a look at a line side, right? Okay, so let's take this one as a feeder. Right? Some people call it a line side, right? Okay, so you have a circuit breaker, right? Yeah. Then you have a disconnect switch here, disconnect switch here. Right? Okay. So this disconnect switch, right, has a insulation, right? And on this side is your shorting block, right? Okay, remember, right? It is shorted and taken to ground, right? Then this one also can be connected to ground. So the removal of this cap or this shorting block is what basically provides the platform for us to perform testing on a GIS. Okay. So now let's talk about testing. Performing testing of contact resistance measurement for a circuit breaker for this line feeder. So you have your micro ohm meter that is located here, right? You have this one connected here, right? This disconnect switch, is insulated from ground. It is floating. Let's call it. It's floating, and only this side is grounded, right? Okay. Then you have this shorting block, right? And you have a cap there. So the shorting, it is in place. It has not been removed, right? So you inject your required current, and it flows through this part, right? Then you have another lead, right? That basically measures the voltage, the return voltage, right? You have an injected current, you have a measured voltage. Then you can determine your contact resistance. Right? Okay, but one thing, the caveat is their contact resistance include the resistance of these switches. Right? Okay, so what you can do is basically find out the factory testing results for this disconnect switches, and basically determine the parallel resistance of this disconnect switches and the circuit breaker to find the actual circuit breaker resistance. Another testing is a breaker timing test, right? Okay, so like I indicated, because the GIS is a complicated equipment, so there are ways and means that have been created, that has been developed to perform quite closer to accurate testing on the circuit GIS. Okay, so we have a circuit breaker. So this is the line side, right? This is the bus side. Okay. Then we have an external connection, right? Remember, early part of my presentation, I made mention that the external connections, the different external connections to the GIS, and I listed them as transformers, right? Where we have oil to SFX interface, right? Then we have overhead line, where we have air to SF6 interface. Okay, so we have a transformer here where we remove basically the connection that goes to the transformer. Okay, so this is our access form. Right? So what they do is basically the jumper, right, is removed. This is the insulated air section, disconnect switch, and this is the section, the disconnect switch without insulated air interface. Okay, so the shorting block, the shorting terminal is, or the jumper is removed. Okay, so another method of performing the breaker timing test is called a dual ground. Okay, so dual ground means that you have both grounding schemes in place, right? And the flexible connection is connected to the power transformer. It is not removed, right? Then you connect your device, that is your dynamic capacitive measurement, right? And you have your ferrite material that is connected on top of the shorting block, right? So the ferrite material, what does it do? It blocks high frequency components from escaping, right? So this testing, basically what you are doing is varying the frequency from low to high, right? And you are measuring the time that is traversed, for the signal to come back. So that is how you are able to perform the breaker timing test utilizing the dual ground dynamic capacitive measurement method. With that comes to the end of my presentation, and thank you so much for your listening ears. And if you like this my presentation, don't hesitate to select the like button in the YouTube, and you can also visit my YouTube channel and also subscribe from my YouTube channel. There's going to be other presentations, much other interesting presentations there. So look out for those presentations coming up, and don't forget to visit my YouTube channel. Thank you so much.